now. Start recording now, and I was just recalling one of the last slides that we saw last time. So this tells you that epithelial cells have all kinds of junctions to keep the cells together, and as well as to keep the cells communicating. And you know that the communication junctions are the gap junctions, these channels that go through from one cytoplasm to the next through the plasma membrane. Remember, they're proteins, right? They're channels. And they're very common and especially important in the nerve tissue, as we will see. Okay, and then we have those mortar ones, the ones that really keep the cells together to form this wall. Because remember, epithelial tissues form walls, from walls of our skin to the wall that it's our skin is a wall to separate and keep all the stuff from the external environment from penetrating. Also the walls of capillaries or blood vessels in general, the walls of those membranes, the serosas that we looked at last time, of the internal cavities, and then lining all kind of internal tissues and internal organs, and the glands as well, we will see, are also formed by epithelial tissues, and that's where we were at last time. So this tells you the process of formation of multicellular exocrine or endocrine gland. They both form initially by invagination, which is this going inward, basically moving inward of an epithelial sheet. Okay, and this is typically a simple cuboidal epithelium that does that. So you see, you end up having mostly for this type of glands, you have simple cuboidal epithelium. Okay, as we saw for the sweat glands. So now what happens is that after this invagination has happened, some glands, so it's an opening, right? Some glands will maintain the opening to the external surface. This could be the external world. This could be a gland that is present really in your skin, okay? And so will secrete to the external world. And in this case, we call it exocrine, because exo means external, so it secretes to the external world, okay, of its own little environment. It could be also an internal, honestly, an internal environment of the body, but it's still external to this duct, okay? Now, in other instances, that duct, as shown here, is lost. That connection to the external world is lost, and therefore the gland really stays inside by itself, isolated. And in this case, we call it endocrine gland. Okay, simple as that. Endo stays inside, and what happens is that this type of endocrine glands get highly vascularized, as you can see here. These red tubes here are blood vessels, okay, represented here, and therefore they will secrete their whatever they produce, because this is a gland. They will produce some kind of hormone, some signal called hormones, and it will be released into the bloodstream and travel through the bloodstream. Okay, so difference very simple. Okay, between exocrine and endocrine glands, remember, they are formed by epithelial sheets of tissue. All right, then I told you to do this exercise for me, okay? And I hope you guys are working on it. I'm still not going to go over it because you have the key, okay? This is pretty simple, okay? And hopefully everybody is able to recognize if any of these image in the test, okay? You're able to recognize. Some of them are really, really easy, okay? Very straightforward, and you have the key here. Don't look at the key before doing your test. Test yourself, okay? All right, so we're pretty much done with all this is all the material that's going to be in the test. Okay, and yesterday I sent a study guide. Did you guys receive it?
Yep.
Okay, let me raise my volume. I can barely hear you. I have my volume real low. And okay, you're welcome. So that's always going to be pretty much the concepts and things that have been included in the test. And for the lab practical, I didn't really do a detailed study guide because really you have to go off, you know, I'm just going to take things from the lab handouts. So that's what, you know, you have to expect, nothing different really. Okay, even the exercises and the conversion, I may just get a few from there instead of, you know, making new ones. So if you have done diligently your handouts, you should be good. Okay. All right. Now what I'm going to do is I'm going to start from chemistry and go over it. You know, go over the main concepts. Okay, that we talked about. So it's kind of like a live review for you. And hopefully, when I would like to maybe leave 10 minutes for questions at the end if you have questions. Okay. All right. So we spent a long time actually on the chemistry chapter. Remember, and we started from the very basics. Okay, because I know that some of you may have come back to school after a while, or you have not even taken a any class, any chemistry biology classes in a long time. Okay, so you really have to start from the beginning, from the definition of matter, which is anything that occupies space, to the 3 states of matter, which is pretty straightforward, to the structure of atoms. And remember, atoms have subatomic particles, which are protons, neutrons, and electrons. And you have to kind of know which ones are like positively charged, negatively charged. Hopefully this time you already remember. And this is a periodic table of the elements. And we learned that there are trends in the periodic table. Most of the elements in nature, remember, are metals. In fact, metals shown here. And then there are the non-metals, a few of them, and which metals and non-metals have different properties, if you remember. And then we have these ones that are on the zigzag here ladder, and they're metalloids because have in-between properties. We learned that there are elements that are essential for the human body, and really what you have to remember for me mostly is this slide over here, which is really the 4. It tells you the 4. Obviously, the number 1 is carbon, okay? But carbon by itself is not sufficient to even define organic compounds. Remember, because something like CO2 is considered organic, okay? It has carbon, but it's an inorganic compound. The other important element to define organic matter is hydrogen. Anything that has carbon and hydrogen together is organic. So a simple molecule like methane, CH4, is in fact organic, okay? So this one, CO2, is not organic, and CH4 is in fact organic, okay? And the other 2 elements, important elements, super important, are mostly present in, was there a question? No, other 2 important elements found mostly in all organic compounds are oxygen and nitrogen. Nitrogen is very abundant in DNA and proteins, is super abundant, okay? So these 4 you have to know very well for me, okay? At least these 4. And then there are others that you cannot know from also. That these are lesser elements, but know that when you buy orange juice, it's addition with calcium, right? You know that's important for your bones. Who doesn't know that, okay? Even my kids know it. Magnesium, you know that it's always present in these supplements that you buy at the store. Iron, who doesn't know that iron is super important? We talked about this, right? When you are anemic, you have a lack of iron. These are really common sense things. Everybody pretty much knows, even people that they don't have an education at all. They all know these things, okay? Iron is very important for your thyroid. Sodium chloride, that's you know, the common salt. Sodium is important, and we have studied the sodium-potassium pump. How can you not remember the sodium is in fact present in our body? Okay, phosphorus, potassium. You know, bananas have a lot of potassium, right? You eat bananas because potassium is important for your body. So these other lesser elements, maybe, you know, try to remember as many as you can, but you don't really have to make an effort. Okay, just think about these common things that things from your everyday life. When you go to HEB and you buy the orange juice and says with calcium, it means it's important for your body, right? And then there are really the ones that are present in trace. Who doesn't know about zinc? Zinc is very much advertised in you know, supplements. Manganese as well, fluorine, you know, for your in your toothpaste, because it's important for your teeth. So it's in your body. Now, the important thing about these trace elements is that most of them, why are they there? Why are they important? Most of them are actually important as cofactors. They aid, they need to bind to enzymes and activate them. That's the key. You know, the more than remembering what they are, but what they do. Okay. And we talk about subatomic particles. We talk about protons and neutrons being very heavy and electrons being very small. They also almost weigh nothing and they're negatively charged. Okay. And we talked about the Bohr model, okay, which is a simplistic model. It's not the truth, but at least, you know, gives you the description of how things are arranged, the subparticles are arranged in an atom. We talked about orbitals, we talked about all these concepts and energy levels. It was important to talk about this because then we can understand by knowing how electrons distribute in energy levels. Then we can understand, I'm going to skip quick on this, why chemical bonds form. That was the very important thing to kind of grasp, okay? And the reason why this form, this is the octet rule, okay? The rule is that elements try to reach stability, and their stability means having either 2 electrons in the first energy level or 8 in any subsequent energy level, generally speaking, okay? There are some exceptions there. And therefore, most elements, we learned that most elements in the periodic table, in fact, are not stable, because when you look at this Roman number, that represents exactly what I said, the number of electrons in the last energy level, which is known as base, right? That's a term you have to be acquainted with, okay? I may give you some questions. We have spend so much time on this and expect questions on these things, okay? So so you glance at the periodic table and you know exactly what this is. So you know what's the status of that element in terms of how many electrons would need, or how many electrons would give it away to reach stability. We learned that these column here, this group, the columns are called groups. It's really the only column of elements that, in fact, are stable. In fact, all these elements don't react, don't form compounds, because they're stable. They don't need to form compounds. Okay, so in a way, in a way, the fact that most elements are unstable is the reason why we exist, because, you know, we are made of complex molecules, okay, that have covalent ionic bonds, all kind of bonds in them. So, you know, if all elements in nature were stable, then life would have never appeared probably on Earth. So this is connected, okay? This is connected to biology. When we talked about isotopes, and you have to know isotopes, okay? These are used in a medical field, and because they emit energy, and we use them for different steps. We use them, for instance, for imaging, and we use them for even treatment of cancer. And you know, the concept here you have to remember and bring with you life and in your career is that they are highly energetic, they are highly unstable, because they have additional particles. The additional particles that they have are the neutrons, if you remember. And therefore, additional neutrons confers a lot of instability to the nucleus. They tend to, and literally these elements that are unstable, they have additional neutrons, they tend to lose them. They want to lose them because they want to reach stability. The principle here is always that you have to think that nature in general, the systems in nature and in the universe try to reach stability, okay? Try to get rid of that extra energy. And if you go by this principle, remember it, you will automatically understand why compounds form, why chemical bonds form, and why isotopes emit energy as well. All right, so talk about all this. This is a review, so I'm not going to the details, right? I'm assuming that you kind of already studied these things, so it's really a kind of like almost watching a documentary today, right? So, okay, so yes, all right. Don't I wouldn't give a class this way, you know, of course. Then we learn how to represent compounds. We can represent them with just a chemical formula, or we can give it a structural formula. These are examples of chemical formulas which will tell you the number of atoms that are in that particular molecule or compound, but they won't tell you anything on how these atoms are in fact arranged. Maybe in this molecule of glucose, right? This is glucose. Maybe there, maybe 3 atoms. I'm just inventing. It's possible 3 atoms of carbon are grouped together, and then that group binds to another group. I mean, it happens all the time. And when you look at a chemical formula, you don't know. If you don't know how really these atoms are bound together, you cannot have any clue about that from this. A different story is a structural formula, where this structural formula tells you exactly how the different groups or the different atoms are bound together. Okay, this is, for instance, an amino acid. Okay, and again, if you were to write the chemical formula of this, and you would just know that there are 2 carbons, you would know that they are arranged, 3 carbons here. They're arranged this way, okay? You may think that they are like, they could be arranged to where they're all bound over here, okay, together. Yeah, there is no clue that you can have from a chemical formula about how atoms really arrange in space. And remember, when you think about a molecule, you have to think about something 3-dimensional. In this previous representation, if you remember, I told you we have a conventional way to represent what's coming towards you and what's going away from you. What's coming towards you is a triangle. Feel the triangle away from you is the dotted line. And so, and this normal the normal sticks here, just thin sticks, means they're on the plane. Okay, so this is a three-dimensional thing, and you can represent it really with a model. You can have you can do it yourself in the lab. We used to do it in school with toothpicks and Play-Doh. You know, you can do that. That's an exercise to create ball and stick models of molecules to really understand that they're really things. They're really three-dimensional things here. All right, so we talked about types of chemical bond. We talked about intramolecular bond, ionic bond versus covalent bond. These are intramolecular. They are pretty strong, although the ionic bond is much weaker than covalent bond. And we learned how in ionic bond, molecules or compounds that have ionic bonds tend to break apart, right, when you dissolve them in water. While covalent bonds are much harder to break. You really need a lot of energy to break them apart. And then we talked about intermolecular bonds, and one of the most important of these types of bonds is the hydrogen bond. It's not the only type of interaction or bond that is intermolecular. We didn't talk about others that also exist, but this is the one that really is fundamental to know about. Okay. And so we described ionic bonds, and we said that ionic bonds form typically between, let me go to the slide, the summary slide already. Oh, wow, I had it. Yes. So typically ionic bonds form between a metal and non-metal. And, you know, that's logical because these are going to be distant in the periodic table to where one of them is going to have, in the bond, is going to have less than 4 electrons. You know that in these cases, it is more energetically favorable to get rid from one atom in the bond to get rid of those extra electrons rather than trying to share them. While in a covalent bond, usually this covalent bond is formed by either a non-metal, typically non-metal, like carbon and oxygen and hydrogen, okay, and or a metalloid and non-metal, okay. You know that when we talk about organic compounds, mostly we talk about non-metal, covalent bond in this case. All right, so this is regarding the two types of intramolecular bond. And then when we talked about this covalent bond, we also made another classification. So not all covalent bonds are the same. Depending on what is the nature of the elements that are implicated into this bond, this covalent bond can be maybe polar, meaning that maybe if one of the atoms that is involved in this bond is a little bit more selfish for electrons, it's going to drive the electrons, pull the electrons towards itself more. This is known as electronegativity, remember, and that creates the situation of a polar covalent bond. Okay. And one of the best examples of polar covalent bond is found in water. And so oxygen is one of the most electronegative atoms in the periodic table, most selfish for electrons. Okay, and so therefore it pulls electrons towards itself. Remember, this is still a sharing, but it's kind of like an equal sharing, we call it. And so this creates a dipole, not just a pole, a dipole, because you have two hydrogen atoms. So two partial positive charges and one partial negative charge in a molecule of water, okay? And that is pretty much a fundamental attribute of the molecule of water, because that determines that therefore there are many electrostatic interactions between the molecules of water and pure water. and that forms like a glue that determines like a force, because, you know, positive and negative attract. Is electrostatic, is what you will find in current. It's like you're acquainted with this. The fact that these are molecules, don't get thrown off by the fact these are molecules. There is positive negative charge, and positive negative charge attract each other in electrostatic fashion, period. Okay, and so these electrostatic interactions are pretty much at the reason why life has evolved the way it has evolved, because, you know, organisms are mostly made of water, including us. Okay, and so that electrostatic interaction, we call it hydrogen bond. This can be very confusing. I wish they wouldn't call it bond, but interaction. I wish that chemistry, you know, would change and call them interactions, because students get confused, because you have the real bonds, which are the ionic and covalent bonds, and then these are not really, you know, bonds that are found within the molecule, it's in between molecules, so they should be called interactions. To me, we should abolish the word bond and call them hydrogen interactions. But I don't decide things, so they're called bonds, and we just have to understand that they are something different than the covalent ionic bond. All right, so I'm going to skip on this one. And so because of this property of water, where we know you have charges, basically there are partial charges, it turns out that if you try to put something in water that doesn't have any charge, this compound is not going to be able to interact with water because it's not charged. Whereas if you put something charged with a charge, then he will really interact and establish these electrostatic interactions with water. That's the concept of hydrophilic, which love water, and hydrophobic molecules. Sodium chloride, because it has this ionic compound in it, ionic bond in it, which is pretty weak. It literally breaks apart in water. And what happens here, there's still a force necessary to break this ionic bond in sodium chloride. And that comes from the fact that there is a liberation of energy when all the ions that come out from sodium chloride interact with water, establish hydrogen bonding with water itself. So that process gives the energy for the sodium chloride compound to be broken apart. And therefore, it's going to be a spontaneous process where you don't really have to input energy in the system. All the energy necessary is coming from the system, okay? It's feeding itself, let's say. So this is a spontaneous process, okay? And this is an example of hydrophilic molecule that loves water, okay, forms electrostatic interactions with water. Then we talk about all the properties of water. This was also in your modules, refresher modules, and you have to know these properties very well, okay? Recognize them and know the definition. Cohesion, it tells you, is the ability of molecules of water to adhere to each other. And again, think about the hydrogen bond as a glue, okay? And therefore, you know already this property. Adhesion is the same thing as cohesion, but this time you're referring to the fact that the molecule of water, because of its polar nature, can establish interactions with other molecules that are also polar or charged, okay? And this is very important in nature, especially we talked about how molecules of water really walk along the walls of this circulatory system that is found in plants. Plants have a circulatory system just like us, okay? Actually, two types of circulatory system. Like we have the blood circulation and the lymphatic system. Plants have something similar, okay? They have to transport water and nutrients up and down. We talked about surface tension. That's another one. The other day, on Friday, I homeschool 2 kids. One of them is mine, and we rotate with other mothers right now because there is no school. I mean, partially, I guess. And we were learning about surface tension. He is in 5th grade, so of course, in a very small and simplified way, but he was learning about surface tension, and and then he was learning about density as well. That's the force that the force that is given on the surface of a liquid, in this case of water, to break into it. And because of the hydrogen bonding, it is pretty hard to break into water. Even some objects can have a hard time to break. And not because this object is necessarily a lower density than the water. That's a different concept. That's what I was trying to explain to the kids. But it's kind of like a little bit hard for them to understand, I guess, at this stage. Anyhow, so there are cohesive forces between the molecules on the surface, which are stronger than the ones that are on the bottom, and that's why this object has a hard time to break through. Animals can take advantage of this surface tension and not. In this case, I think insects deposit their eggs without sinking into the water. That's very important. So the very super important consequence of presence of hydrogen bonding, and this reconnects to the homeostasis chapter that we studied just recently, is that water is able to moderate changes in temperature highly. It's very it's the best of the solvents, if you will, to do so. And that's because of the presence of hydrogen bonding. If you want to heat up water, it takes a lot of energy. You have to put that pan of water for quite a while on heat in order for it to change state, to go from liquid to vapor. In vapor, you have disrupted all the hydrogen bonds. In liquid water, you have lots of hydrogen bonds. You give energy, heat energy to that system, is absorbed, and it takes a long time and quite a bit of energy, heat energy, to disrupt the hydrogen bonds. And once you have disrupted the hydrogen bond, that's when the water goes to the gas, the state of gas. And so that's one example that makes you understand how much energy can the hydrogen bond retain. When the water cools down, therefore releases a lot of heat energy, and this is for instance, if you can appreciate this, if you take a bath, for instance, in the bathroom, and then you leave that water, you see that after a while, the bathroom itself feels so much warmer because the water is cooling down and it's releasing a lot of heat energy in cooling down. So it absorbs energy when you want to heat up, and it releases that energy when you cool it down. And you can appreciate this phenomena in your everyday life very easily. Now, because of all this heat energy that water can conserve, it turns out that in homeostasis, in maintaining body temperature, there is an SOS system in place where if your body overheats, there is a system in place where your sweat glands can be activated to release a lot of water whenever the body temperature is too high. And if you think about this, this is not logical in a way, because, okay, if you are in a situation where you're overheated, maybe and then you keep losing water, maybe you lose too much water at some point, if you're like in a desert. But remember, these systems are always in place to compensate for the best outcome. At some point, if of course you lose too much water, you may go in a situation where the body shuts down because it doesn't have enough water anymore. But initially, when the body tries to compensate the temperature change, the overheat, that's the most efficient thing to do. Release water. Okay, that's what happens, as we learn from the negative feedback loop involved in regulation of temperature, body temperature, right? We just saw that the other day. All right, water evaporates slowly because of hydrogen, and there is a glue there, and so kind of like it takes energy and time to disrupt this glue. And the ice floating, that's another property, and the fact that ice has less density than water itself, as you can see here. That's because in ice all the bonds are formed, and the bonds, hydrogen bonds, have a certain length, certain distance to them, and so now you have this lattice, we call it lattice, that is formed, and the density itself is less than in liquid water, and that's why the ice floats. And that's not something common, because usually the solid form of a set of metals, for instance, is more dense. All right, so water is an excellent solvent for hydrophilic molecules. We already talked about this, whereas it's not a solvent. It does not dissolve hydrophobic molecules, which are molecules that have no charges whatsoever. They're neutral, and therefore, or partial charges, and therefore they don't mix with water, okay? And we know these are oils. All right, a little bit of time maybe we should spend in reviewing the concept of pH. Okay, I bet everybody's happy about that. Now, as I told you, in order to understand what pH is, you have to start from this slide. This is the very most important slide. If you don't start from this concept, you don't grasp it, what this pH is. Okay, this is a fact that you have to learn. If you don't learn this fact in this slide, your pH is going to be something that is just an abstract thing. You don't know exactly why we use it and where it comes from. So pH comes from the concept of water dissociation. What you have to know is that in pure water, there is always a certain percentage of water molecules that, and it's always the same, we talk about pure water, that dissociates in ions, specifically in hydrogen and hydrogen ions and hydroxide ions. Okay, that's a fact, and they have measured this, and they have said, and they have measured that in pure water, obviously these two are equal because they come from one molecule of water, and the concentration is always 10 to the minus 7 molar. And molarity is just a measure of concentration. Okay, molarity is number of moles per liter of a certain substance. All right, so 10 to the minus 7 scientific notation is a decimal, right? It's 1 over what? 10 million. And that's something you have to be very acquainted with. We use scientific notation all the time, especially in representation of pH. If you don't recall, it's just simple, right? The scientific notation, you're going to have problems here. Is this a negative 10 to the minus 7? Is it a negative number or is it a positive number? Anybody? Ooh, I'm glad I asked this question. I have 1 positive and 2 negatives. Another positive. Let's see what's come. It's just really small. I like that answer. Yes, Kiet. So the winners are Jessica and Kiet. I like those answers because It's a real small number. It's absolutely not negative, guys. Don't get confused. It's not a negative number. 10 to the minus 7 is 1 over 1 with the 7 zeros, right? Which is 1, 2, 3, 4, 5. My zeros are so bad, sorry. 1, 2, 3, 4, 5, 6, 7. So it's a decimal, okay? You can also write it as 0.000000. One, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7. Okay, am I right? 1, 2, 3, 4, 5, 6, 7. So this is it. And so it's not convenient. Would it be convenient to write this number over and over, and I have to count my zeros, and then my eyes start going like all over the place because I can't? What if I have 10 to the minus 15? I have to write 15 zeros. Oh, I can't do that. So scientific notation is just a convenient way to represent these very small decimal numbers, okay? But it's not a negative number, okay, guys? Don't make this mistake. And so it's a convenient way to represent these small decimal numbers. And when we talk about water dissociation, because we're talking about something very small, the fraction of molecules of water that dissociate is so small. It's 1 in 10 millions, right? 1 over 10 million. And so it's good it's convenient to use the scientific notation, but it's not a negative number at all. Okay, so you start from this knowledge, and then you wonder, okay, this is pure water, okay, where I have this concentration. But what happens if, for instance, I put a substance in pure water that disrupts this concentration? So this 10 to the minus 7 can go up or can go down, depending on what kind of substance you are mixing with water. And that's when the concept of pH comes, okay? And remember the definition of molarity, okay? So measure concentration, though. If it's really hard for you to understand molarity, just remember this for me, is a measure concentration, period, okay? So we move on, and we define the pH. Now it's scary because it's you see a logarithm here, and you didn't like logarithm at school, right? But you don't have to worry about it, okay? You don't have to understand. Again, the logarithmic scale here is used for convenience, just as the representation of a small number in scientific notation, okay? What you need to know is that because of this formula here, just do it on the calculator. If you don't like it, just you have the calculator. I guess you don't have the logarithm scale calculator in your respondus, but you don't need it, okay? You need to know the trick here. You need to know how to extrapolate the pH from a given concentration of hydrogen ions. So we focus on the concentration of hydrogen ions in the definition of pH just because by convention. We could focus on the concentration of H minus. Nobody says that we couldn't, okay? But by convention, we decide to focus on that. And, you know, in pure water, you know that OH minus and H plus, they coincide, that the concentration of the two coincides, and is equal to, again, 10 to the minus 7 molar. And as I told you, there are substances that disrupt this equilibrium. They either reduce or increase the concentration of your hydrogen ions. That's the whole key, okay? And so there are the substances that reduce your H plus at the concentration of your hydrogen ions, that reduce it. We call them, what do we call them? If your hydrogen ion concentration is reduced, what do we call those substances? Bases. Very good. Base. Let's start from this concept, okay? The substances that increase your hydrogen ion concentration, what do we call them? The ones that decrease your H plus concentration, acids, very good. They're bases. I'm going to put a B here because it's so hard to write. The ones that increase your H plus concentration, instead we call them acids, okay? Now, because of the logarithmic scale here of the representation of pH, it turns out that the deviation from, if you apply, let me delete everything. If you apply this formula, the pH formula, to pure water, just get the calculator, if you have a scientific calculator, and do the anti-logarithmic logarithm of 10 to the minus 7, you'll see that that is 7. Okay, that's it. Now, for what we have said, there are substances that can reduce or increase this concentration of H plus, okay? And it turns out that if you reduce this concentration, what's going to happen if this concentration is reduced? What's going to happen to the number 7? Is it going to increase or decrease its number? Or we can say this concentration. Because of the logarithmic scale, what's going to happen to that number? If I decrease the H plus concentration, which somebody says correctly is known as a base, this substance, what's going to happen to that pH number? Increase or decrease? Become higher than 7? Yes. So a base is a substance that reduces the H plus concentration, the hydrogen ion concentration, and increases the pH over 7, right? And vice versa. An acid is a substance that increases the H plus concentration and reduces that number 7. So that's the whole key. And as I told you, whenever you are in front of, if you are given the concentration of hydrogen ions in scientific notation, like here, this is pure water, your pH corresponds to the exponent, the pure exponent, okay? 7. 7 is the pH of pure water, and we call it neutral, okay? So if you're given, again, let's practice. If my concentration of H plus, okay, equals 10 to the minus 11 molar, always put the unit of concentration. What's your pH? 11. As immediate. It takes a fraction of a second to answer this question, okay? Yet, so many students get it wrong. Or there could be tricky answers. I could say minus 11, and many students fall for it. Remember, it's always a positive number. pH is always a positive number. Don't get thrown off by that negative exponent, okay? There. You have to know how to immediately extrapolate the pH value from a given concentration of hydrogen ions, okay? Now, if I wanted to be really mean to you, you know what I would do? I would give you a question where I give you the hydrogen ion concentration. Instead of in molarity, I would give you in millimolarity. What would you have to do? Would you have to take an extra step here? What would you have to do? If the concentration of hydrogen ion was in millimolarity, you know, when you talk about pH, your unit is molarity. What would you have to do? Convert it first, okay? It's simple, but yes, very good. But I'm not going to give that to you because because I think that it's going to be a mean thing to do. Okay, or maybe I will give it just because, you know, I noticed some students, you know, to differentiate between a student that deserves an A and a student that, you know, hasn't studied as much and maybe will not get it right, you know, but you have to know how to do these tricks, okay, if you work in a lab, absolutely. All right, so pH, power of hydrogen, okay, you look at the concentration of your hydrogen ion, and your pH is that little number there, okay? Simple as that. Most of the time in your exercises, you're giving already the scientific notation. Maybe another little bit mean thing I could do to you is not give you the scientific notation. I'll say pH, or I would say the hydrogen ion concentration equals 0 or 1 times 0.001. What's your pH? You just have to do the little conversion representation of your very good, okay, 3. You just have to represent this number in scientific notation first. If it's not immediate for you, that you look at it and you already know, you just go ahead, take it step by step. That's why you're gonna have your scrap paper there, okay, to do these little things there. Here, this could be more an exercise that I give you in the lab practical. Whenever you convert scientific knowledge, I myself, I have to count. If I don't count, I may get it wrong, okay? You have to move this decimal to after your integer number here. So 1, 2, and 3. So this is 10 to the minus 3. If I don't count, sometimes even if there's many zeros there, I gotta count. Like, you know, it's not that, you know, my mind is like this great mind that I can look at something and I have to count. Otherwise, if there are 10 zeros there, my eyes go like, whoa, what is this? Let's count, okay? And then you get it right. You get it right if you do it in a, you know, with a certain criteria. Things, don't rush them. Write it down. Count the places. Write your number, scientific notation, you know the pH, okay? All right, so let's move on. I guess we spent a lot of time on pH, acids, base, and salts. We pretty much already defined these two. Salts are substances that don't have an impact on pH whatsoever, okay? And I already told you what acids and bases do. And the one important thing that's super important here is the concept of buffers. And I also told you, sorry, another differentiator between weak and strong acids or bases. Basically, the strong ones are the ones that completely dissociate, and weak ones are the ones that don't completely dissociate. I think I have a more visual thing here. See, this is a strong acid because completely dissociates in water. You see they're all ions here, while something like H2CO3 does not completely dissociate. See, there still are some molecules that are intact, okay? And typically when you see an arrow in one direction, it's a strong. When you see either a double arrow like this, or one arrow with two heads, you're talking about weak, okay? Let's move on. I want to move on to the This is the summary. Well, the pH scale, okay, here is important, okay? The scale goes from 0 to 14, okay? The neutrality is 7, okay? And everything that is between 7 and 14 is basic. Everything that is less between 0 and 7 is acidic. Some very acidic substances are shown here. Then we talked about some important acids and bases in the body, okay, like hydrochloric acid, carbonic acid. Why carbonic acid is super important is it forms actually the buffer system in your blood, as we talked about. And I think I have a dedicated slide to that. Now, what's a buffer? Okay, you must know the definition of buffer. Basically, you have to, conceptually, you have to understand a buffer is a substance that, that opposes to changes in pH, okay? That tries to fight the changes in pH. This means that if you try to increase the concentration of H+, it will release OH minus, or vice versa, okay? You have to compensate for that. So if you know the general concept, you're able to recognize what's written here, okay? So, so when the pH increases, so H plus decreases, your buffer will release H plus, okay? And vice versa. All right, then we talked about the most important buffering system in the human body, the bicarbonate system. This is a little bit screwed up, this slide, but it's okay in your PowerPoint. It's just the way it comes out in the Blackboard Collaborate. And so bicarbonate ions and carbonic acid form this system, which maintain a pH around 7.4. That's the set point, and we know that it can oscillate, right? Between 7.35 and 7.45 as we learn. This is the bicarbonate buffer system. So carbonic acid, which is a weak acid, will dissociate in a bicarbonate ion and hydrogen ion. And this is a base. So in this system, there is an acid and a base. And so because this is a weak acid, as you can understand from the double arrow basically here, things can go back and forth as necessary, okay, in order to maintain that hydrogen ion concentration at a certain level. That's what defines the pH, right? So that hydrogen ion can be absorbed. And these two can associate. When there is formation of carbonic acid, you are depleting your blood of H+. If you're depleting your blood of H+, what are you doing to the pH? If you deplete, reduce, means reduce the concentration of H+ in your blood. Does everybody agree? It becomes more basic, which means increases the pH. Perfect, okay? Don't get confused, okay? All right, so, okay, we're done talking about pH, and then we talked about chemical reactions. We talked about pretty much 3 types of reactions, and then, you know, reactants, products, I'm just giving you know what they are. We talked about synthesis reactions, which can be represented this way. Something is being synthesized, basically. This is true when long chain molecules form in your body, proteins, DNA chains of acid, nucleic acids. So, for instance, proteins are made of units known as amino acids. Okay, these are the anabolic, as we call them, anabolic reactions in the body. And decomposition reactions, which are typically the catabolic reactions, is when a molecule is chopped down. For instance, we talked about the regulation of sugar in your bloodstream, remember that there is a double loop there. There isn't just your body doesn't just always want to reduce the concentration of glucose in your bloodstream. There are moments where you are starving. If a person is starving and needs glucose, the opposite happens. So the reserve of glucose, which is this long chain molecules known as glycogen, it needs to be chopped down, and in that case that's a decomposition reaction, okay, and that's catabolism. It's a catabolic reaction. Okay, and that's exactly what I was talking about. This is glycogen made of many units of glucose bound together, which is going to be chopped down to the single units. Exchange reactions, so they can be represented this way. There is something that moves, okay, moves around. That's what it means. And we gave kind of like an example of an exchange reaction with ATP. ATP does lots of exchange reactions where, you know, the ATP, TP stands for triphosphate. Remember, this is the energy currency of the cell. We saw how, when we talked about channels many times, this third phosphate group, in fact, is transferred, remember, to the channel and then a conformational change happens. In this case, it's just a reaction that is shown how one phosphate group could be passed on to a molecule of glucose, for instance. And so there is an exchange, okay? One phosphate group gets from ATP onto another molecule, and ATP becomes ADP, becomes diphosphate now. It was tri, now it's di because it's lost one phosphate, right? Okay, so then we talked about mixtures, and we talked about homogeneous mixtures, which are the solutions. We talked about, I'm gonna skip on this one. We talked about suspension. Best example of suspension is blood, because of this, all these heavy particles that settle down, which are the red blood cells. While the plasma itself is a solution, okay? Only the plasma by itself. And then we talked about these weird solutions, which are the colloids. Milk is an example of colloid, but also the cytoplasm is an example of colloid, which has all these macromolecules in it, but they don't really settle down, okay, like in suspensions. And sometimes these can acquire a jelly-like, this colloid is a jelly-like consistency. And then there are all the emulsions, which are obtained when droplets if you try to mix two substances that can really mix together, and you have the formation of these emulsions. And you could kind of or let's say that in the human body, emulsification happens, okay? Happens because there is a substance that's produced in your body, which is bile, that has a function to emulsify large droplets of fat that end up in your body. By doing so, it's very important because now the smaller droplets can be digested more easily. Simple, okay? Keep it simple. All right, so I'm pretty much done with chemistry. I've already 10:07. Oh my goodness, I just went over chemistry. So let me upload real quick the chapter of cells. Is it me, or this slide not in our PowerPoint? I'm gonna double check on that. Okay, let me double check on that. Emulsification, is that possible? I have added. I think you're right, you know, because now I'm trying to remember, and I think that some student asked me about emulsification. That's why I added it. I added it later, but I forgot to replace the PowerPoint. Do you need me to add it? I mean, it's here. Is in the, do you want me to replace the PowerPoint? I'll do it. So let me, yes, you're welcome. Add files, cells. So I guess I'm going to just very quickly go on the chapter of cells because homeostasis and the chapter we just finished it, they're very recent, okay? So, okay, it's almost done. Replace chemistry. Okay. Oh, it's converting. It is uploaded, but it's converting. My goodness. Taking forever. In the meantime, I could do the replacement since it's converting. I'm going to do the replacement of PowerPoint so I don't forget. Okay, it's ready. All right, so oops, share now. All right, so we talk about the major component of the cells of a cell, and all what we talked about really is important. Okay, I minimized really, but so just the main function of these organelles that we talked about. Now, the most important one, though, is going to be the plasma membrane, okay? The most important component. You know why? Because we talk about transport, and it's all connected there, okay? So I'm going to skip on this one. Remember the endomembrane system, which mostly really we talked about rough endoplasmic reticulum, which is like this packaging facility in this big factory, which is the cell, right? And after the packaging facility, there is the FedEx dispatch, which is the Golgi apparatus, and there is a lot of vesicle trafficking between the two, right? Because all these goods are not just sent out like without having a good box, being contained in a good box, right? Which is your vesicle, okay? So very conceptual here. And we talked about the digestive system of the cell, which is the lysosomes, which are also vesicles. These vesicles contain these little machines that break down everything that needs to be recycled, okay? And typically there is a fusion. Remember that all these vesicles, all these membrane system, they have a phospholipid bilayer there to delimitate them, define them. And so phospholipid bilayer fuse very easily with one another. So any vesicle can fuse with the plasma membrane very easily, or two different types of vesicles can fuse with one another just because there's the same thing, they're composed of the same thing on the surface. So phospholipid bilayer. And of course, phospholipids is something you have to know very well. For me, what's a phospholipid, okay? We talked about cellular extensions, and we talked about these extensions, especially cilia and microvilli, where we talked about epithelial tissues. You know now why I presented this, because obviously, you know, they're relevant to anatomy, and when we talk about tissues, we know some tissues present microvilli. And remember, cilia are the functional cilia is to move substances, propel substances across the surface of a certain tissue. Microvilli are meant to increase the surface area for absorption. We just we talk about flagella. There's only one type of cell that is flagella in the human body, and these are sperm cells. All right, so we talked about cytoskeleton. There are different sizes of filaments, but remember that cytoskeleton forms like a support skeleton inside the cell to maintain its shape. And then we talked about the fluid mosaic model of the cell membrane. This is super important, okay? And remember that there is a phospholipid bilayer that composes the plasma membrane as well as all the endomembranes as well. It's always the same thing. And we represent phospholipids like this way with a head and two tails. The head is hydrophilic because it's negatively charged, and the tails are hydrophobic. So you have an hydrophobic barrier here. It's almost impenetrable. It will only be penetrable by those molecules that are hydrophobic. But is it penetrable to water? Yes, okay. It's one of the few substances. What are the other substances that can pass through very easily? Examples of them, molecules that can pass through this barrier very easily are water, of course, and then oxygen and CO2. Very good. Okay, I want you to remember those. Those are important. And a few others that are hydrophobic, such as cholesterol or sex hormones that derive from cholesterol. Anyways, okay. So remember this, and water can flow through directly through the phospholipid bilayer small enough, or through specific channels known as aquaporins. This is also something you have to remember. Now, the membrane doesn't just have phospholipids. Embedded in the membrane, there are proteins. That's why this is called mosaic fluid model. And we talked about these proteins. So you can define them by location as integral proteins or peripheral proteins. There is a slight difference between the two. Transmembrane integral, they span the whole membrane. For instance, channels must be transmembrane integral, because if it's a channel, it needs to be kind of spanning the whole membrane, while if it's a receptor, maybe it can be just an integral, can be just kind of embedded halfway through. Okay, so these are just definitions, and more importantly, we talked about the functions of all these plasma membrane proteins. You have to know them all. Okay, we talked about transport. This is super important, and there are several channels and carrier proteins. Channels typically are passive. They just, let the substances diffuse through, while carrier proteins, usually they utilize energy. We talked about examples of this. We have proteins on the plasma membrane that are pure enzymes. We have receptors that are bind the external signals and elicit a response inside. We have proteins that are meant to do cell recognition or intracellular joining, such as, now gap junctions, tight junctions, and desmosomes. These are all proteins that are present on the plasma membrane. And proteins that will attach to the extracellular matrix or even to the basement membrane. You know what a basement membrane is now, right? Or you haven't studied yet, but we have mentioned the basement membrane in epithelial tissues. When a cell attaches to the basement membrane, to this fibrous material, they're all proteins, it attaches through plasma membrane, okay? Plasma membrane proteins, sorry. And so the most important chapter here was on transport, and again, you have different types of transport, and then in this regard, we talked about, I'm skipping this because I already talked about all this briefly. So we talked about passive transport and active transport. You must know the difference between the two very, very well. And of course, we have done an entire lab on this passive transport. Now, passive transport is not just diffusion. There are other types of passive transport, okay? Diffusion, but also osmosis, which is super important, and hopefully everybody understands what is osmosis at this point. filtration and facilitated diffusion. Okay, real fast. Okay, diffusion, we all know what it is. You know, substances diffuse, move from where they're more concentrated to where they're less concentrated. But when you are in front of, and there are factors that influence diffusion, as we will see, as we saw, there are sometimes, like in the case of cells, you have substances that cannot pass through a certain barrier, which is a plasma membrane, but water can pass. In that case, what happens is that a phenomenon known as osmosis, which is the diffusion of water. If a solute cannot pass, water will pass, and that's osmosis, and they will pass to kind of try to equalize the concentrations of the solutes in the two compartments. That's the concept of osmosis. This happens in cells. Okay, let me go directly to the cells, and then we talk about tonicity. Okay, if you put a cell in an environment where the concentration of solute is the same as the intracellular fluid, ICF, then nothing happens because the movement of water is equal in and out. There is not a static situation there. Okay, it's always a movement that it is happening, but it's happening in equal amount in and out. Whereas if I place a cell in an environment where the concentration of solids is low, it's hypotonic compared to the intracellular fluid, I will have osmosis happening, passage of water and from the external environment to the internal intracellular fluid, or vice versa. If I put a cell in an hypertonic solution, water will move out, okay, to try to dilute the external environment by osmosis. And you know, this is swelling here. Cell will swell, eventually burst, and this we know it as shriveling, cell shriveling. Okay, and so these were some examples. You have to be able to recognize what's going to happen in these situations. Okay, we kind of did the exercise. In your handout, it also talks about, especially red blood cells. There's the best system to appreciate what happens when, especially when the cell bursts, because you can appreciate in a test tube where you have a suspension of red blood cells. When cells burst, the suspension becomes clear, as you have learned from your handout. So you know indirectly, even without looking at a microscope, that the cells have bursted. So you can appreciate the osmosis process by looking just at what happens when you put red blood cells in hypertonic, isotonic, or hypotonic solutions. All right, we talked about then filtration that happens in the kidneys. We were talking about filtration also, not yesterday, on Tuesday. We're talking about filtration when we were talking about what kind of epithelial tissue is present here in the renal corpuscle to favor I'm gonna highlight it here, to favor, maybe in green, red on red. What is this tissue? Look at it. It's one cell. It's mashed down like a fried egg, and it's one layer of cells. So what do we call this one? Let me look at the answers. Somebody may have got it right. Squamous. So Diana is and Evie are correct, but is it stratified or simple? It's one. Look, it's one layer of cell. Okay, it's so easy. This is the easiest to recognize. It's a simple. And why is there such a simple one layer smashed cells? Because the filtration has to happen very quickly. Okay. You see how we're talking about a process here, and it reconnects to a structure. Everything here is connected. You have to know everything if you don't know the premises, and you know, if you have understood filtration very well, and remember we talked about this, we talked about this, at this point, it should be very easy to remember where, an example of where squamous, simple squamous tissue, epithelial tissue is present, okay? Everything is connected here. And by the way, it's so easy to recognize, isn't it? Like a smashed fried egg looking cells on one layer, simple squamous. All right, so, ooh, it's already 10:24. You know what? If you guys need to go. What I'm going to do is I'm going to at least finish this chapter of cells review, so you have it recorded. And then I'm not going to open up the homeostasis chapter and the intro to AMP because we have done it just recently. This is more the material that was a little bit old already for you. So that's why we're going over it, okay? So I'm going to finish this, especially the diffusion and facilitated diffusion and active transport, because it's important. And then I'm gonna stop it. But if you need to go, just go. So feel free. I mean, you don't have to hang out with me right now because we are already out of time. Okay, this was a review. And I mean to also send this recording to my other classes where actually they weren't as lucky as you because we missed the one lecture with them. We missed the holiday, the Labor Day holiday, so I couldn't do a review with them at all. So I'm gonna send them this recording in case they wanna watch it. All right, so we talked about two types of carrier-mediated transport. One refers to as a facilitated diffusion. The other is active transport. And active already implies a consumption of energy. These are the properties of these carriers. And remember that no matter what, most of the time, what happens with these transports is a conformational change that within the transporter itself. It's not the transporter, it's just right there. The transporter very dynamic, it's very dynamic, and by binding something on one side of the membrane needs to change its conformation to make it go through and open up at the other side. That's always the mechanism, okay? We talked about examples of facilitated diffusion. We talked about the example of glucose transport through the plasma membrane of red blood cells. That's an example of facilitated diffusion, which means that there's a channel there, but the transport and the passage of glucose in these through this channel is passive. There is no energy involved, okay, in this particular mechanism. So that's a good example of facilitated diffusion, okay? Other small amino acids also can pass through the plasma membrane, through the carrier's plasma membrane with this mechanism. Then we talked a lot about active transport, where now ATP is energy is utilized in this type of transport. And this type of transport is the example where you're pushing the molecules against or up their concentration gradient. You're moving a substance from where it is less concentrated towards where it's more concentrated. It's like pushing that rock uphill. So that's why you need an energy input here, okay? And again, in this type of transport, even more so, your transporter always undergoes a very dramatic conformational change because it will bind something on one side of the membrane. Then there is typically a transfer of phosphate group from ATP to the transporter. How do we call this type of reaction? We just saw it 5 minutes ago. When you transfer a phosphate group onto a molecule, or in this case it's a transporter, it's still a molecule. It's a big complex molecule. What do we call this type of reaction? Is still somebody there? We are still 11 students. Anybody? We just talked about the 3 types of reactions. Is it a synthesis reaction? Is it a decomposition reaction or is it like an exchange reaction? Nobody wants to try? It's an exchange reaction. Remember, we just saw it. You are transferring one group, a phosphate group from ATP to another molecule. Okay, anyways, after this addition of phosphate group, there is a conformational change. So the carrier now closes on one side here, closes, you see from this goes to this, and opens up on the other side. That's always the same thing that happens with these transporters. So the most important of these active transporters that you have to remember for me, if you don't remember this, you're not going to get some points in the test, is the sodium-potassium pump, okay, that we described. And remember, in this pump, sodium and potassium are transferred in different directions. It's the same pump that has evolved that has two sides. One side will pick up sodium, the other side will pick up potassium. And remember here, the key thing that you have to remember is where towards which compartment is sodium transported. Remember, sodium must be maintained low inside the cell, in the intracellular fluid, and therefore is pushed outside, okay? And if you remember that, and you remember potassium goes the other direction, you know, potassium is maintained high inside the cell. So this is a very clever, simple, really, mechanism where in the first step, the pump will bind sodium, okay, this binds sodium, and at that point, ATP is consumed. There is a transfer of phosphate group from ATP to the carrier itself. The carrier that has picked up sodium will close on the inside and open on the outside, releasing sodium. At that point, it's open to the outside, so it picks up potassium and literally speeds or releases potassium to the inner intracellular fluid, the inside environment of the cell, into the cytoplasm, okay? Believe it or not, it looks complicated, but it's really simple. After you have studied it, it should be pretty simple, okay? So this is something to be known very well. This pump is very important in the nervous system, as we will see. Then we talk about secondary active transport. In this secondary active transport, basically there is what it looks like a passive transport that happens here, but in reality it's not, because it harnesses the energy from that is being utilized in a different transport process in conceptual terms. And by giving examples, probably you have understood better what we're talking about. If you have a sodium pump that uses active ATP, but creates a gradient of sodium, concentration gradient of sodium, that concentration gradient has a lot of potential energy. It's like the rock up the hill. Now, if you have a carrier through which sodium can pass, that is going to be a diffusion, right? Because it goes from high to low concentration. If somehow that transporter can also let another molecule or ion go through it, then now you are an example of secondary transport, okay? Simple as that. And this is the sodium-calcium cotransporter example that we gave. Another example is the sodium-glucose transporter, okay, which is known as SGLT, S sodium GL glucose T transporter. That's a good example of secondary transporter, because there are some cells in the body that not all the cells have this type of simple facilitated diffusion transport that we talked about for that was happening for the red blood cells. Red blood cells have facilitated diffusion in the transport of glucose. Here we're talking about other types of cells, especially intestinal cells, okay? and they rely on this secondary transport to transport glucose concomitantly with sodium. Okay. All right. So these were like, this is the whole picture basically, which is also represented in the next slide, of how you can have coupling basically between different type of transports and at the different surface. This is one this is the apical surface of this cell, okay, and this is the other the other side of an intestinal cell, okay. On these two sides, the plasma, there's a plasma membrane, right? The plasma membrane can have different transporters that will transport things in different directions, okay, because here you want to absorb, this is the lumen of intestine, for instance, okay, you want to absorb, and here you want to release in the bloodstream substances, okay. And so glucose has to be absorbed here, and then it has to go from here inside the cell, but then it has to be transported outside to the bloodstream. And so this whole process here is coupled, okay, with the sodium-potassium pump, and utilize the energy of the sodium-potassium pump to accomplish this, okay. All right, so then we talked about vesicular transport. Definitely this type of transport all utilizes ATP. We talked about endocytosis and exocytosis, okay? Endo coming in, exo going out. And we talked about phagocytosis. It's very important that big things are phagocytes, even entire organelles, or big chunks of food, or entire organisms, such as a bacterium, okay, can be phagocytes. And then pinocytosis refers to cellular drinking, and small droplets being phagocytes, I can say phagocytes, being incorporated. And then we talked about the receptor-mediated endocytosis, which is a phenomenon that happens in particular sections of the plasma membrane that are coated. And regarding this third process of receptor-mediated endocytosis, this is important, especially when viruses get inside cells, certain viruses such as HIV. Then we talked about transport of cholesterol, which is also an example of receptor-mediated endocytosis. Now we talked about exocytosis, which is sending out the membrane, plasma membrane substances. And again, remember this principle here is that any vesicle can fuse very easily with the plasma membrane and release its content outside. All right, and then the last thing here, this is a part 2 that you have. I have put it together so that I don't have to open another lecture, but this is the cell part 2 that you have uploaded on your Blackboard. We talked about cell communication, and we talked about long and local communication and long distance communication. In local communication, the first thing that should come to your mind are the gap junctions that we talked about. And there are other types, which are the content-dependent signaling, where just the receptors on two cells that are adjacent, they take contact and initiate signaling in the two cells. We talked about examples of this in our defense system, immune system. And then we talked about other two types of local communication, where some substances can be released by some cells and act on cells that are adjacent through binding to receptors, or even cells can auto-stimulate. So this is known as paracrine, the first example. Cells can stimulate themselves, okay? And that triggers more and more stimulation. This is known as autocrine signal, where now, instead of as in the first example, one signal acting on a cell that's in the vicinity, the signal acts on the very cell that has produced it. Okay. All right. So then we have long distance communication, which we just talked about endocrine glands just a little bit at the beginning of this presentation today, because we finished that slide. Endocrine cells, endocrine glands, we learned that are vascularized and so release their hormones inside the bloodstream, and these hormones will act on cells that are pretty distant in the body, can travel pretty much a whole body sometimes through the bloodstream. That's an example of the long distance communication. But another example of long distance communication is also given by these neurotransmitters, as we will see that they're released by certain types of neuronal cells, and they have to travel a gap. It can seem a small gap to you, but for a molecule to go through that gap, it's like traveling the whole world. Okay, and then so if you want to have a parallelism there, so it's a long distance. Another example of long distance communication. Okay, there are also neurohormones. Okay, that are released in the bloodstream by certain neurons, as we will see. They also travel through the bloodstream, so really long distance. Okay. And we talked about, so what happens in a cell signal, all these instances where there is a signal that is released by some types of cells and reaches others. What happens in the cells that receive this signal? Typically, they have a receptor on the plasma membrane, because some of plasma membrane proteins can be just receptors. And what happens is that once the binding happens, this activates an intracellular signaling pathway that goes through typically many intermediate molecules to trigger a response. And we learned that most of the time this response happens at the nuclear level, because changes that have to happen if factories have to decide to produce different proteins. The managers have to decide what's the managing department of the cell that takes the decision of which product, which are the protein, have to be made is the nucleus. So it makes sense that all the signaling, the message of, look, that's what is trendy right now. You have to produce these products. These are the important products that will sell and will be useful in the body, right? So the nucleus, okay, that's the target usually of this signaling. Sometimes, as we learned, there are hormones which are signals, right? Signals that are released. They are not proteins, but they're lipidic. And because they're lipidic, they don't need a receptor to come into the cell. They can go through the plasma membrane directly, and many times really go straight to the nucleus and activate the target genes. For instance, the estrogen. What does? It does have a receptor inside, the estrogen receptor, but that's it. It will come into the cell, bind to that estrogen receptor that finds inside the cell, travel to the nucleus, and directly activate the genes that need to be activated. All right. So, whereas in many other cases, your ligand, your hormone is a protein, and so it needs to bind on the plasma membrane, and that binding will trigger a response, a cascade we call it. Okay. And we gave briefly some examples of this type of intracellular response. Sometimes you have your receptor acts as an enzyme itself, and that enzymatic activity intrinsic to the receptor is the activity that will, the first activity that happens to perhaps break down a molecule, and that breakdown will be passed on as a signaling cascade to end up into the nucleus. Or some other time, your receptor receptor is bound to a certain molecule. In this case, it's shown as showing a G protein. We'll find these G proteins in the nerve system, so we'll talk about them again. I don't want to overwhelm you right now, but this was just like an introduction. This G protein will then activate an enzyme that will cause an intracellular response. It's just a little bit more complicated, okay? In the simplest case, you have here that your ligand can even, once it binds, in the first case here, it lets some molecule pass through that a particular channel, and that particular substance that is moved inside will elicit the intracellular response. Okay, so pretty much I talked about this in general, so I'm going to skip here. And just wanted to give you an example of a receptor enzyme. Best examples are protein kinases. Are called kinases because a kinase adds a phosphate group to another molecule, basically, in an enzymatic fashion. And these are very common, okay, as receptor enzymes. Again, there is a cascade, a molecule activate another molecule, another molecule, another molecule, and finally you have your final product that typically ends up into the nucleus to kind of change some gene activity there, okay? And then we talk about G protein coupled receptor, which are these receptors that are coupled to these proteins known as G proteins, which there are two major types of them, CMP, second messenger systems, and phospholipase C. And that's all I'm going to tell you. Okay, that's all I wanted you to kind of try to remember these two names, because we'll find them again when time comes and we study the nervous system especially. All right, being a little tired myself, I'm going to stop here, okay, for review. We did all chemistry and cell review. These were the longest chapters and the more the chapters that we did more farther back in time. Homeostasis we did recently. I think is pretty interesting and easy to understand with examples. Then you have the terminology, the chapter on terminology, body directions, regions, things like that. These are very straightforward, really just learning. And then we just did epithelial tissues, which is pretty descriptive as well. Okay, so I'm gonna end here. I only have 4 students, but that's okay. And the others of you that have to leave can definitely listen to the recording. Okay. Do you guys have any questions? Those of you that are here, still here? You're welcome, Jessica. And yeah, exam is on Monday, but you have many days to still study, okay? All right, so I'm going to stop the recording.
So just to be clear, the test opens 9 a.m. on Tuesday morning?
Yeah, I think 8 a.m. already open, 8 a.m.
Oh, okay, awesome. Thank you.
I'm tempted to not leave it until midnight, because some of you will take the test last hour, and you guys are tired. I don't know. I think it's gonna be you're not gonna perform as good if you're so tired in the evening, you know. Some of you are tempted to take the test, so you want to study more and more and more during the day, probably. But I've experienced that some students will take the test at 11, you know, just the last hour, and I don't think it's a good idea. So I was tempted to not leave it until midnight, to leave it maybe until 10. Yeah, and that's a good point. I was about to say, but I know that some of you work, and so you may have just a late hour stay. So I will leave it until midnight, okay? From 8 a.m. to midnight. Okay. Thank you, Jessica, for your inputs today. Appreciate it. All right, so stop recording and I'll see